Okay, this is what I would like you to do on tonight's homework. Basically, I'm going to ask you to use the first solution that you get through applying the Frobenius method and use that first solution in order to find a second solution. And you're going to be doing that using the techniques in section 2.1, reduction of order. I'm going to go ahead and review that right now with question number 3 from the homework. I worked through number 3 to find the first solution in a video that I posted yesterday. So it's section 5.3, question number 3, and you can find the video for that posted on Canvas. The equation was xy double prime plus 2y prime plus xy is equal to 0. This turned out to be a case 3 because when we found the indicial equation, it had roots of 0 and negative 1. Now, in last night's video, I went ahead and plugged in the root of r equals 0, and we went ahead and solved the infinite series, and this is what it came out to be. y1 was equal to a naught sine x over x. So that's our solution 1. Now, in reality, the y1 is really this part. The coefficient of a naught is just the constant that allows us to plug in boundary conditions. Remember, this is a general solution, not a particular solution. So we're just going to call y1 the sine x over x for the purposes of the next exercise. What we're going to do next is kind of determine what y2 is by performing the following calculation. y2 is really y1 times the integral of 1 over y1 squared e to the negative integral of p dx, and then the whole thing has a dx for the outer integral. Px is determined by the original differential equation when it's in standard form, and of course standard form means dividing through by x, so px is the coefficient of the center term, and that makes it 2 over x. So px equals 2 over x. So now we're ready to start solving this. I'm going to basically build it from the inside out. So the first thing I want to do is find the integral of p dx. And of course the integral of p dx is going to be the integral of 2 over x dx. That's a natural log, so it's 2 ln of x. And of course using the rule for logs, that 2 becomes the exponent, so it's ln of x squared. And now we see what we do with this is this becomes the exponent on e that goes inside this integral. So I'm going to evaluate e to the negative ln of x squared. Well, the negative can also go up as part of the rule for exponents in logarithms. So that's going to be e to the ln of x to the negative 2. And then, of course, another rule for logarithms is e to the natural log is just the argument of the natural log. So that's x to the negative 2, or 1 over x squared. So this entire part of it right here is just 1 over x squared. What I want to do now is multiply that by 1 over y1 squared, and I want to integrate that whole thing dx. So what's inside the integral is 1 over y squared, and that's just going to be the reciprocal of this. So it's x squared over sine squared x, and then that's times what this exponential turned out to be. So that's 1 over x squared dx. So the x squareds cancel, and 1 over sine squared is the same as the integral of cosecant squared x dx. Oh, the one thing I'm forgetting is, no, that's actually it. So cosecant squared x, the integral of cosecant squared is cotangent. There's no argument, there's no coefficient in front of the x. If there was, we'd go 1 over a and all that stuff, but there isn't one. So it's just cotangent of x, and I think it's negative cotangent x. So there's a negative introduced here, but I'll show you later. I can just absorb that into the constant. Again, none of these require a c because we're going to add the constant on as part of the fact that this gives me y2. So I don't need any constant as part of any of these things. So there it is. So that's cotangent, and that's the result of the integral. So now to find y2, I just have to multiply by y1. So y2 is equal to y1, which is sine x over x times cotangent x, and it's really negative cotangent x. Well, cotangent x is cosine over sine, so it's sine x over x times cosine x over sine x. And these cancel, and I just get negative, the negative was still there, I just get negative cosine of x over x. So this then forms the basis of my solutions. This is the second solution, there's the first solution. So this differential equation, whose first solution came as a result of applying the Frobenius method, its entire solution is y equals a naught sine x over x plus, and I guess we can call the second one b naught, and it's going to absorb the negative because b naught can be anything, so it may as well absorb the negative, cosine x over x. And there it is. That is the entire general solution to this differential equation. And I didn't have to apply the case 3 rule, which was to substitute in that fairly awful y1 times logarithm plus a second infinite series. That would have also yielded this answer, but it would have been a lot more work to get there. So this is a much easier way to go. Especially if this integral is easy to perform, then there isn't any reason not to go this way in finding the second solution to these differential equations that we're going to solve through the Frobenius method. Really, the only time I wouldn't go through this way, the only time I would actually work with the infinite series that comes with case 3 second solution, is when the px in the function was so complex that it's not going to produce anything simple here, or when the y1 doesn't reduce to a function but remains an infinite series, because this is going to be a pretty unpleasant integral to perform if I have to divide first by an infinite series into an exponential function. So nonetheless, forming this integral is one thing, solving it is another. We're going to reserve this for the times when these are easy to solve. Okay, for the homework tonight, you are going to then apply this technique to questions number 5, 9, and 11. 9 is a case 1, so you'll be able to use the infinite series twice. There isn't any sort of strange second series that you plug in. 5 and 11 are both, I believe, no, 5 is case 2 and 11 is case 3. But once again, for all three of these, you could use this technique to find the second solution once you have the first solution. So you will have to go through the work to find the first solution to 5, 9, and 11, just the same way we did for number 3 in last night's video, the same way you did in last night's homework when you tried to work through those 4 problems, finding solution 1. You're going to basically do that for 5, 9, and 11, and then use this technique to find the second solution. All right? Okay. Good luck. These problems are not simple, but you'll get great satisfaction from doing them right.